Can hear you now.
Yes, we can start.
Are you able to see my slides?
Yes, we can see.
Okay.
We can start. Yes, thank you.
Okay. So, thank you all for the invitation to speak. And so, because we have so much time, what I want to do is I want to do a nice, gentle introduction to the subject and talk a little bit about an area that I have worked on with students for many years. And one of the things I love about this area is the prerequisites to start quite low, but there is a lot of very interesting questions that very quickly lead to some advanced mathematics. Some of these questions can be resolved by some very painful brute force calculations, but if you look at them the right way, the problem becomes significantly simpler. A lot of these, we know the right way to look at problems, but we don't know it for all of them. So I'm really hoping that some people in the audience get interested in some of these and talk to me further about additional problems that one can do. Okay, so let me start. And so just a little bit of background about myself. So I've been guiding undergraduate research for over 2 decades now, and we have something called the REU program, Research Experience for Undergraduates. And so the biggest questions are always to try to figure out what is worth asking. And depending on the background you have, this is going to be very different. One of the advantages I've had is I've been trained both as a mathematician and as a physicist, and that helps me find good perspectives, good questions to ask. And that trying to find that right perspective for these problems. Originally, a lot of the results I'm going to mention was proved using number theory techniques involving continued fractions and the like. But it turns out it's a lot easier to attack these problems by changing our point of view and looking at these as combinatorial problems. And so this comes on to the next part is utilizing what tools do we have, how can we attack these problems? Okay. And so if I had to describe my research philosophy in a sentence, it would be the law of the hammer. If all you have is a hammer, everything looks like a nail. And there's 2 ways to look at this. The first is if you're really good at something, no matter what problem you're given, you find a way to convert it to what you're good at, and then you just hammer away. But an even better way is to take the skill set that you have and move to the land of the screwdriver. If they could have solved it using the screwdriver, they would have. They're smart people. And so a lot of these results come from the fact that my students and I have attacked some standard old problems from a different perspective than other people working in the subject. And so I'm going to start off.
Excuse me, Stephen.
Yes.
Can you switch on your video, please? Is it okay?
I really can't put my video on here because the internet connection on my house is not great.
Okay, please. Okay.
But that's why I'm just trying to keep it on the slides. So we unfortunately live in.
Can you close the end screen with you there?
Trying to just minimize the screen with you guys. How's that?
Yes. Yeah, now it's working. Yeah, thank you. Yeah.
Okay. Yep. Okay. I'm sorry to make sure. Okay. So let me start off with the I Love Rectangle game. And so the way it's played is for each integer n, we have exactly one n by n square. And we want to place these down on the plane one at a time, such that at each moment, there's always a rectangle. So you can't put a tile on top of another tile. And so I've done this game going all the way down to kindergarten classes. So I do a lot of math outreach. I do a lot of travel trying to get people excited about mathematics. And I tell the students, I tell the kids, if you can place 2 of these squares down, you win. And so very quickly they realize that this game stinks, that there's no way you can take 2 tiles and place them and still get a rectangle, because if you place something that's say 5 by 5, then every other tile is either going to have a shorter or a longer side, and there's no way they can align. So in order to make this game interesting, I have to give you at least 1 more tile. And the cheapest thing I can do is give you a 1 by 1 tile, an extra 1 by 1 tile. And so now, you should notice the pattern that's going to come in. We take the 1 by 1 tile, We put the other 1x1 tile next to it, and we now have a 1x2. We can now place our 2x2 tile. We now have something that's 2x3, we place the 3x3 tile. We now have something that's 3x5, we place the 5x5 tile, and so on and so on and so on, and we see the Fibonacci spiral. And so this is a example I made out of fuse beads with my daughter. We then made it, a little bit larger. And so this is a great way to start getting, young kids excited about the Fibonacci numbers, finding patterns. There's a lot of, theorems you can prove here. What's nice is you can actually prove that the sum of the squares of the Fibonacci numbers up to n is the nth times the nth plus first by calculating the area different ways. So this is a very nice geometric proof, beginning to see some properties of the Fibonacci numbers. So I want to talk about some deeper properties of the Fibonacci numbers that you may not have seen. And so the prerequisites is just some basic probability. So I don't need to know too much. I just need to know what is a random variable with a density, what is the mean, what is the variance. And for most of the talk, we'll just need two distributions, the Gaussian, the normal, the bell curve, and then we'll also need the exponential distribution. And then for combinatorics, we actually don't need anything too advanced. We just need, n factorial is the number of ways to order n people when order matters. We need n choose k, the number of ways to choose, k from n when order doesn't matter. And then we need Stirling's formula. We need to be able to approximate n factorial pretty well. And so, we've mentioned, the Fibonacci numbers before, and when we were looking at, putting down the tiles, you see each one is the sum of the previous two. So you get the sequence, 1, 2, 3, 5, 8, and so on. And there's a beautiful theorem due to ZeckDecompGames that every positive integer can be written uniquely as a sum of non-consecutive Fibonacci numbers. So there's a lot of ways to prove this. So for example, if I give you the number 51, the easiest way to prove ZeckDecompGames' theorem is actually constructive. Not only will it prove the theorem, but it will tell you how to find this decomposition. And the goal of the talk today is to understand as many properties of these decompositions as we can. So the simplest proof is the greedy algorithm. We take a number like 51 and we subtract the largest Fibonacci number less than or equal to 51, which in this case is 34, which hopefully you see is now highlighted in red up above. And we're left with 51 equals 34 plus 17. And then we just do shampoo mathematics, lather, rinse, repeat. We do this again. What's the largest Fibonacci number less than or equal to 17? Well, that will be 13. So we then subtract 13, we then write 17 as 13 plus 4. And 4 is not a Fibonacci number, so we keep doing this again. We keep doing this again. And eventually we have our decomposition. And then it's not so bad to show that if you have two different Zeckendorf decompositions, they can't be of the same number. And it's not too bad to show that this algorithm is always going to work. So every number has a unique Zeckendorf decomposition. And hopefully my accent is not too hard for you to understand. But more than just my Boston accent for English is how I'm choosing to define the Fibonacci numbers. A lot of people define the Fibonacci numbers as 0, 1, 1, 2, 3, or 1, 1, 2, 3. I'm defining them as 1, 2, 3, 5, 8. And the reason is we want to have a unique decomposition. And if we had two ones or a 0, we would lose that uniqueness. As a nice, strange property, speaking of accents, if you take your Zeckendorf decomposition and you shift every index up by 1, so we would take our F8 and shift to F9, our F6 and shift to F7, we convert from the number 51 to 83, which is approximately the shift from miles to kilometers. And this is just a strange coincidence that the golden mean is almost the same as the ratio from miles to kilometers. This is a nice, fun exercise. Right. So now we're at the point where we can start talking about some results that most people have not seen about these decompositions. So we showed every number has a Zeckendorf decomposition, and the Zeckendorf decomposition is unique. If we were to look at other recurrences, not every number would have a decomposition, and not all the decompositions would be unique. But in the Fibonacci case, it is true. We can now look at what is the distribution of the number of summons. And there's a couple of ways to look at this problem. I'm going to look at the distribution for integers m between the nth and the n plus first Fibonacci number. And the reason I'm going to do it this way is because by forcing my numbers to be in the interval from Fn to Fn plus 1, they all have to have Fn as their largest Fibonacci in their decomposition. So in some sense, I'm comparing apples to apples. If I looked from 1 to Fn, I could have some numbers that are small, maybe around 100, and some numbers that are very large around Fn. And so because you're small, you just can't have that many summons. You have at most your largest index divided by 2 because we can't have adjacent terms. And so this just forces everybody to be somewhat comparable. It's not hard to go from one to the other because the Fibonacci numbers are exponentially increasing. So if I go from Fn plus 1, if I want to go from this all the way down to the integer 1 to the start, well, once I move down about log n intervals, I have captured essentially 100% of all the numbers, and there's really not that much of a difference between Fn and Fn minus log n when I'm trying to count the number of summons. These intervals are extremely similar. So it doesn't really matter which one you look at. It's a matter of personal preference. I just like to have everybody in the same interval. And so you get a beautiful Gaussian behavior. So there are way too many integers between 2010 and 2011. So you just choose a bunch of random ones, and you got an almost beautiful Gaussian. The next question you can do is not just what's the distribution of the number of summons, but what's the distribution between gaps between summons? If we look at a Zeckendorf decomposition, how often do we see a gap of length 1, a gap of length 2, a gap of length 3 between adjacent summons? Well, the Zeckendorf decomposition is writing our number as a sum of non-adjacent Fibonacci's. So we know we're never going to have any gaps of length 1. But what about gaps of length 2 or 3 or 4? And so one way to do this is, we look at our decomposition. So I'm writing M as a sum of Fibonacci numbers. And then I'm going to use, the standard notation of delta for the Dirac delta function, which is going to be 1 when x is equal to ij minus 1. So it's going to basically just count, going to give me a mass every time I have that as a gap. And so I can do this for each individual integer m in my interval, and I can see how often do I have a gap of length 2, 3, 4, and so on. That's a little bit of a hard problem. It's much easier to look at an average problem. So if I average over all m, how many of the gaps are length 2? How many are length 3? How many are length 4? We can actually prove that the result below holds both on average and almost surely for each individual m in the limit. It's just a little bit easier, and it requires less technical stuff to prove it on average. So that's what we're going to focus on today. So the result is that these gap measures converge almost surely to a geometric decay, where not surprisingly the decay constant is the golden mean. And so on the left, the picture's worth 1,000 words, is a plot of a histogram of the distribution of the gaps for the numbers from the previous page. Sample of numbers from. This is there's a typo that should. Apologies. When you look at it, it's kind of hard to see the geometric decay. It looks approximately geometric in terms of the size of the probabilities as I march down. So it's much easier to plot the ratio. And that's what the plot on the right is. It's looking at the ratio of the probability of a gap of length, k, divided by the probability of a gap of length k plus 1. And if the theorem is correct, we should see something that is very close to the golden mean. And if you look at the plot, you should be able to see that. One of the things that's interesting, and hopefully the zoom in will work, is you can see as k increases, it actually stays pretty close to the golden mean for quite a while. And then there seems to be some interesting behavior towards the end. Now, once k gets very large relative to n, we're now in a situation where we don't expect to have that many gaps, and now being off by 1 or 2 could cause some interesting behavior. If you've ever looked at convergence to the golden mean of ratios of Fibonacci's, It makes a difference if you're looking at even or odd indices to start things. And so if anybody's interested in exploring, I think there's some interesting stuff to look at with how things are forking at that picture on the right. One thing that I definitely don't want to go into this morning is, it's a little bit more technical, is the distribution of longest gaps. So I am teaching probability this semester. My first class is in just a few hours. I'm hoping to be awake for that. One of the experiments that is required in America whenever you teach a probability class is at some point you ask everybody to flip 100 or 200 fair coins and record the results. And half the students are supposed to actually flip the coins, and the other half are supposed to just simulate it. And then as a professor, you're supposed to be able to tell who did it correctly by flipping the coin and who just made something up. And while students are usually pretty good about making sure half the time it's heads and half the time it's tails, people do not have a good understanding of the distribution of streaks of heads and tails. What's the number of alternations between heads and tails? What's the longest run of heads or tails? And so this is a really nice, fun problem, and we can actually prove similar results as to what you would see with flipping coins in looking at the longest gap between summits. It's a nice double exponential. And so I'm not going to go into the details of that, but if anybody's interested, there's some really nice papers, some nice complex analysis comes in to proving these results. So what I wanted to do now is just talk a little bit about this new perspective I promised. So I started the talk today by saying that the law of the hammer is best used when you go to the land of the screwdriver, when you have a new way of looking at things. As a number theorist, I should have liked a lot of the standard proofs on the subject. They're using number theory, but to me, I really view this as a combinatorics problem. And so what I want to do is I want to explain the combinatorial input we need. So I call it the cookie problem. A lot of people call it the stars and bars problem. So it's if we have C identical cookies and we have P distinct people, how many ways can we divide the cookies among the people? So in this situation, all that matters is how many cookies do you get, not which cookies you get. And the answer is just C plus P minus 1 choose P minus 1. So I'm going to give you the proof. Hopefully you all have seen Sesame Street. This is hopefully a global phenomenon. One of my favorite characters is Cookie Monster. I'm actually wearing a Cookie Monster shirt right now to remind myself to speak highly of him. Cookie Monster is a Muppet who always loves to eat cookies. And if you ever need cookies to be eaten, he is there. And so imagine the case when we have C plus P minus 1 cookies in a line. And Cookie Monster now comes and eats P minus 1 cookies. Well, if he eats P minus 1 of C plus P minus 1, then we're left with C cookies. And so by eating P minus 1, that's partitioning our set of cookies, of our C remaining cookies, into P sets. So for example, let's give an example where we have 8 cookies and 5 people. So I'm going to write now 8 plus 5 minus 1 is 12 cookies on a line. Cookie Monster shows up. And let's say Cookie Monster gobbles up cookies 3, 4, and so on. Everything up to the first eaten cookie goes to the first person. So the first person gets 2 cookies. The second person, it's not their day. They get no cookies. The next person gets 2. The next person gets 3. And the last person gets 1. So there's a 1-to-1 correspondence between the number of ways Cookie Monster can eat P minus 1 cookies from C plus P minus 1 and the number of ways of dividing C identical cookies among P people. So this is a quick proof of this result. What we're really doing is we're really solving the Diophantine equation. This is the standard problem of we want to count how many ways can we write an integer as a sum of non-negative integers. We can no longer do such combinatorial proofs if we were doing things like sums of squares or sums of cubes, but for sums of first powers we can. And this is going to be extremely useful. And so let's see how we can use this to prove Zeckendorf's theorem. So we'll let P and K count the number of integers from Fn to Fn plus 1 whose Zeckendorf decomposition has exactly case summons. So what we're doing now is we're splitting the integers not by where they are in the interval, but by how many summons they have. Do they have one summon, two summon, three summon? We know everything has to have at least one summoned. They have to have Fn. So we can write our number as a sum of Fibonacci numbers, where we have some results about the indices. The indices can't be adjacent, and the last index has to be little n. So one should never do too much algebra in public, in a talk. It's always dangerous, especially when you're doing it at 4 a.m. So, my goal here is to just give a highlight of the idea. Don't worry about following the details, too much. Hopefully you can just see that everything will work out if you do it carefully. And so what we're going to do is we're going to take the indices and we're going to rewrite them based on the constraints that are forced upon us. So we know I1 has to be at least 1. We know I2 has to be at least 2 more than I1 and so on. And so what we're going to do is we're going to introduce some new variables. We're going to do a change of variables. We're going to let D1 be I1 minus 1. We're subtracting off what we know about I1. And then DJ is the gap between the J and the J minus first indices minus 2, because we know it has to be at least 2. And then a little bit of algebra shows that the sum of the D's is n minus 2k plus 1, and the D's are greater than or equal to 0. Well, this is just the cookie problem. We know how many choices there are. So if we want to have exactly k summons in our decomposition, the number of ways of doing this is n minus 2k plus 1 plus k minus 1, choose k minus 1. And when the dust settles, you just get n minus k, choose k minus 1. So we are extremely fortunate here that we can count exactly how many integers in the interval from Fn to Fn plus 1 have exactly k summons in a Zeckendorf decomposition. It's n minus k, choose k minus 1. And now we can prove Zeckendorf's theorem if we remember a nice fact about binomial coefficients. That if we sum these binomial coefficients over k, where k goes from 1 to n halves, then we get the n minus first Fibonacci number. So that would be enough to prove the theorem, because we know two Zeckendorf decompositions can't be the same. And if we count how many Zeckendorf decompositions we've created, if we see that this number is equal to the number of integers in the interval from Fn to Fn plus 1, then that means every number has to have a Zeckendorf decomposition. Conversely, if you accept the greedy algorithm proof that we had from before, this provides a new way of proving this binomial identity, that the sum of these binomial coefficients is a Fibonacci number. Okay, so now let's talk about the proof of Gaussian behavior. How do we know that the number of summons as we vary m in the interval converges to a Gaussian? So the reason I've been using the number 2020 is my students and I proved this result back in 2020. The result was known using other proofs beforehand, but our proof generalized to some new cases. And what was interesting is I actually announced the proof before my summer students arrived on campus, before they even started working on the problem. One of my colleagues had been talking about related problems, and I realized if we adopted a combinatorial perspective, that we would be able to solve problems like this. And so I reported at Mel Nathanson's conference in New York City in May that my students would be proving the following result, but I don't know yet exactly how far they can push it. And what you will hopefully see is that the proof that I knew they would come up with works, but is absolutely painful and is screaming at us to try to find a better way of looking at things. The proof is also not going to be very easy to generalize, because it's using this result that we know, a nice closed form expression for how many integers in the interval have exactly k summons. If we look at related problems with other recurrence relations other than the Fibonacci numbers, we unfortunately don't have such an expression anymore. But for the Fibonacci numbers, we have that. So the main idea is just use Stirling's formula, to approximate these binomial coefficients as n goes to infinity and show that that converges to a Gaussian. So that's the one-line high-level proof. And then this is where it was nice to have lots of students, so I gave them the problem to do the algebra. It makes the algebra a little bit nicer if you look not from the interval fn to fn plus 1, but from fn plus 1 to fn plus 2. And then the number of integers is going to be fn. So we now look at the binomial coefficient n minus k, choose k, and then we divide by the number of integers in our interval, which is fn. And that's going to be the probability that we have a integer with exactly k summons in the interval from fn plus 1 to fn plus 2. I don't think anybody wants to go through the algebra in detail. I have posted the slides on my homepage. So if you just search for the name of the conference under the talks tab on my slides page, you will be able to get all these, or you can look at the papers. It's basically just plug in Stirling's formula to expand the factorials, and then do a careful job pulling out the n's and the k's, and just keeping the main terms and taking the limits. And so unfortunately, we need a little bit of knowledge about k. Well, if we have n summons, we know the largest k can be is n over 2, because the best we can do is have every other. The worst it can be is 1. And so you might think, well, maybe on average, it's somewhere between those two extremes. Maybe it's around n fourths. And the mean is actually very close to n fourths. The heuristic is actually pretty good. So with a little bit of work, you can show that the number of summons is on the order of some multiple of k, and the standard deviation is on the order of square root. Is on the order of the number of summons on average is on the order of n, and the standard deviation is on the order of square root of n. So it's somewhat tightly around that. So anyways, we just look at our expression. We can break it up into the product of two terms. The first term is not too bad to analyze. The second one is a little bit more involved because it has our expressions n minus k and n minus 2k and k raised to powers depending on k. And we need to take those limits. The first term is very nice. It's just a square root. That's not too bad to analyze. So as I remarked, we just write k as mu plus x sigma, where mu is the mean. That's going to be on the order of n. Sigma is going to be on the order of square root of n. And so x is going to be on the order of like 1, 2, 3. It's going to be a small number. Absolutely fine to say that the probability that x is greater than log n in absolute value is negligibly small. Chebyshev's theorem is enough to do calculations like this. So without loss of generality, we can assume we just need to look at situations where x is, at most on the order of, say, log n. Then we just, plug everything in, and we just start doing the algebra. And so here C is equal to mu divided by n, where mu is the mean. So it's basically the multiple we have. And you can show without too much trouble, it's about 1 over the golden mean plus 2. And so I'm not going to go through all the algebra. Whenever you have products, you should have a Pavlovian response of taking logarithms, because the log of a product is the sum of the logs. And then we can use Taylor series to expand the logarithms. And then it's just doing the algebra. And so it's a little bit painful, but we constantly rewrite things, keeping track of which things depend on n and how. And so if I have a term like, x sigma over mu, which we see in a few places, or x sigma over n minus mu, we know mu and n are of size n. The difference is going to be of size n. Sigma is of size square root of n. X is of size at most log of n. So this expression is going to be, at most of size log n over square root of n. So when n gets very, very large, this is very, very small. This is very, very close to 1. So when we expand it out, we really only have to keep the first two terms. Once we get to the third term, it's going to look like at most log cubed n over n to the 3 halves. And even when we hit it by large things like a factor of n outside, it's still going to be something of order log cubed n over square root of n, which will be negligible in the limit. So this is just to show you that all we have to do when we expand out is just keep the first two terms and just not make any algebra mistakes. And again, this is where it was nice to have 4 students. Eventually we were able to, go through the algebra without making an error. There's several pages of just straightforward calculations. It's not pleasant, but it's not that difficult. It's just keeping track of all the expansions, and then just looking at what happens, and then at the end of the day, you can start to see the Gaussian coming in, the -1/2 x squared sigma squared, and then just putting in what everything is, and then when the dust settles, you end up with the Gaussian. So this proves the Gaussian behavior, but this is not going to generalize well to anything else. And it was crucially using the fact that we had a closed form expression. And so what I want to talk about now, and again, if anybody's interested, I'm happy to invite you to join me in looking at some research questions related to this. I have the honor of serving as the president of the Fibonacci Association, so these problems are near and dear to me. So we could consider a more general recurrence relation, C1, HN, and so on and so on and so on. It turns out that for a lot of these problems, not only must the C's be integers, they must be non-negative integers, and it's essential that the first coefficient, C1, is positive. If C1 is not positive, it can happen that you no longer have every number has a decomposition. It can happen that numbers do not necessarily have unique decompositions. But in the case when the C's are non-negative integers and the first one is positive, we do get a generalized Zeckendorf theorem. Every positive integer can be written uniquely as a sum. I don't want to go through in full detail what does it mean to have a legal decomposition now. For the Fibonacci numbers, it was just no index is ever repeated, and we never have two indices next to each other. Roughly, the generalization is I can't use my recurrence relation to reduce things. So if I had, my recurrence relation was, 2hn plus 3hn minus 1, I can never have 2 followed by 3 in a row because I could use my recurrence relation to replace that. We have Lekircher's theorem again, which is just that, on average, the number of summons is just some constant times n. And we do have, Gaussian or central limit behavior coming again. And so I mentioned Lekircher's theorem that the number of summons is, converging to some multiple of n on average for how many summons we have. The expressions become a lot more involved. What's nice is we can write down exactly what that constant is in terms of the coefficients of the recurrence relation. So we do have nice formulas, but they do become far more involved as the recurrence relation gets harder and harder to analyze. We do, as I remarked, have a generalized Gaussian behavior, and what we do is we just count how many indices, how many integers do we have for our decompositions. And so rather than giving you the full rigorous proof of how the Gaussian theorem generalizes, let me try to give you some intuition as to why it's true. And what frequently happens is there's a problem that we're interested in, and we start studying it, and then eventually we realize we're looking at the wrong problem. So rather than looking at how many summons do we have in a generalized legal decomposition, let's look at not a general recurrence, but a simpler recurrence. So rather than the Fibonacci's, let's look at hn plus 1 is just 10 times hn. This is going to give us decimal expansions. And so what we're going to do is we're going to count, if I look at all the decimal expansions between numbers between, say, hn and hn plus 1, how many of them have exactly k summons? Well, that's just essentially saying how many of them have the sum of their digits in their decimal expansion equal to k. Well, we can actually prove that this converges to a Gaussian by the central limit theorem. So if we think about what's going on, if we let AI denote how many times we have 10 to the I in the decomposition, then the AIs are just independent, almost identically distributed random variables. All of them range from 0 to 9, except the largest, which ranges from 1 to 9. Well, as our number gets really large, one index being slightly different is not going to matter. And so the central limit theorem just kicks in and says that the sum of A2 plus A3 plus AN, these are independent, identically distributed random variables that converges to a Gaussian, and the mean is just going to be 4.5 times n the variance is going to be 8.25 times n, so the standard deviation is going to be on the order of square root of n. And so this gives us some intuition as to why we get these Gaussian results in these other settings. One of my favorite formulas in all of mathematics is Binet's formula. Assuming most people have seen something like this, where we can write down an explicit closed form expression for the Fibonacci numbers. To me, I always find generating function arguments like this miraculous. You start off with the recurrence relation, Fn plus 1 is Fn plus Fn minus 1, and you form the generating function where you sum the Fn x to the n's. And somehow, because we know the recurrence relation and we know the first two values, we do know all the Fibonacci numbers. So the hope is that when we construct this function, we can actually write down a closed form expression for g of x. And once we have a closed form expression for g of x, we can use that to deduce information about the fn's. And the way it's going to work is we have our sum, and let's just look at the sum from index 2 onward. And then I'm just going to write it as Fn plus 1, Xn plus 1, just to make it a little bit easier to substitute. So we then use the recurrence relation. We replace Fn plus 1 with Fn minus 1. And now the two sums on the right, well, it's a little bit strange because you have different powers of x than the index. So let's pull out an x from the first term and an x squared from the second. So now everything is going to have the same index. And so now when we do that, we see that these are almost the same as the function g of x. The first one on the left is just missing the n equals 1 and 2 terms. The first one on the right is just missing the n equals 1 term. So we can just subtract those off. And then we can solve for g of x. And we get g of x as x over 1 minus x squared. So we now have a closed form expression for g. And using this, we want to deduce what the f's are. So your first thought might be to use the geometric series formula and write this as x over 1 minus r, where r is just x plus x squared. Unfortunately, if we do this and then expand using the geometric series formula, it's not going to be pleasant because r is not homogeneous in x. It has a term of degree 1 and a term of degree 2. So when you expand it out, it's going to be a nightmare to try to isolate how would you get the coefficient Fn? What we do is we use partial fractions. And so we factor the denominator as 1 minus alpha x, 1 minus beta x, and we can expand. And when we do that, we can now write it as a nice difference. And now we can use the geometric series and expand. And when we do that, we're going to get a much cleaner expression. And this is how you get Binet's formula. So the idea is to build these generating functions using the recurrence relation. And then if we can get some nice closed form expressions for these generating functions, we can use it to deduce information about our coefficients. And that's going to be how we attack things in general. So the two ingredients we need from probability is a very standard tool, differentiating identities. And so if I give you an infinite sum, frequently we can differentiate term by term and get a new identity. And this becomes a very powerful way to calculate certain moments in probability distributions. So for instance, if f of x is 1/2 x plus 1/4 x squared plus 1/8 x cubed, this is basically the weights, the coefficients here are the geometric random variables probabilities. It's geometric random variable with probability 1/2. If I take the derivative and then set x equal to 1, this is actually just going to give me the expected value of a geometric random variable with probability 1/2. And so this shows the power of this technique. It allows me to calculate the first moment, I could calculate the second moment, and so on and so on. And then the last result we need is the method of moments. That if things are nice, if you know your moments are converging to the moments of the Gaussian, then you should be converging to a Gaussian. And of course, it's not enough for the moments to converge. Sadly, there are examples of probability distributions that have the same moments but are not identical. So you need a little bit more than this, but roughly this is what's going on. And so we just need to show that the moments are converging to those of the Gaussian, and the 2mth moment of the Gaussian is 2m minus 1 double factorial. So that's just the product of every other term all the way down to 1. And so let me show you just briefly how we set things up. So again, we want to count how many integers in the interval have exactly k summons. So I can look at my decomposition. And again, we're going to look at the interval fn plus 1 to fn plus 2. So I have to have the summoned fn plus 1. And now here's a nice way to look at it. So pn plus 1, k plus 1 is going to be how many numbers in this interval have exactly k plus 1 summons. Now, I know I have to have fn plus 1. And then where's my next summoned? Well, if my next summoned, it can't be fn. It could be fn minus 1. It could be fn minus 2. It could be fn minus 3, and so on and so on and so on. If it's fn minus 1, then that's equivalent, when I'm looking at how many ways to fill in the rest, as counting how many integers have exactly k summons where their largest summon is fn minus 1. And that's just going to be pn minus 1k. Or maybe the second largest summon is fn minus 2. And then it would be the same as counting how many numbers have exactly k summons where their largest summoned is fn minus 2. And this is why I was writing k plus 1. And so I now have this formula for how many integers have exactly k plus 1 summoned. Unfortunately, this recurrence relation grows. And so I have more and more terms, which is annoying. But there's a standard trick. I can look at pn k plus 1, and I will have its expansion. And then if I subtract, I get pn plus 1 k plus 1 is now going to be a finite recurrence relation with just 2 terms. And this isn't going to be too bad to analyze. And so we can actually form a generating function for these numbers p and k, and there's a closed form expression. So unfortunately, because there are 2 indices, it's a little bit more involved. We have 2 variables now, x and y, but we do have a closed form expression, and we can play games, we can pull things out. And so I'm not going to go through all the details, but you can do the differentiating identities, you can do the method of moments, and you can use this to prove all the different results. To just show you how bad things get, and my appreciation to my students who sloughed through these calculations, the Fibonacci formula is not too bad, just nice 2 simple terms. The general case is much more involved with a lot more indices and sums and powers. The generating function for the Fibonacci is not too bad. It's just y over 1 minus y minus xy squared, whereas the general case is far more involved. And the students did a monumental job, doing all of this analysis. And then, at the end of the day, you are able to show that you get Gaussian behavior. All right, so what I want to do now, since I believe we have an hour 15 or an hour and a half for the talk, I want to briefly talk about gaps in the bulk, and then we'll shift to games in a little bit. Can you confirm how long the talk is? Is the talk an hour and a half?
You have another half an hour.
Another half an hour, okay. So let me just quickly talk about gaps in the bulk. And so if I look at a Zeckendorf decomposition, I can look at the distribution of gaps between indices, between summons. So for instance, if I have f1 plus f8 plus f18, the gaps are 7 from 1 to 8 and 10 from 8 to 18. So if we let p and k be the probability that we have a gap of length k, does this limit exist? So as n goes to infinity, how many times do we have a gap of length 2 if you look over all integers in the interval? And so instead of doing things for Fibonacci's, you could do things for other recurrence relations, you could do things for binary decompositions, and so on and so on. And what my students were able to prove a couple of years ago is essentially it's geometric decay, except maybe for the smallest gaps, depending on which recurrence relation you're looking at. And so for the Fibonacci numbers, you can't have repeated indices, you can't have adjacent ones, so we don't have the j equals 0, the j equals 1 case. We only did the case when all the c's are non-negative. The more general case is a little bit harder. No one has actually gone through and dealt with the case where some of the c's are equal to 0. The algebra is just getting a little bit more involved. If anybody's interested in a research project, please ask me. This is definitely something that can be doable in some cases. And so let me give you a proof for the Fibonacci case that you have geometric decay. So by Lekukkur, we know that the number of gaps, the number of summons on average is n over phi squared plus 1. The number of integers in the interval is fn minus 1, so the total number of gaps is just the product. And now we just need to make sure we do a good job counting. So let's let xij be the number of integers whose decomposition includes fi and fj, but nothing in between. And so as I range over all m in my interval, this will tell me how many times do I have a gap of length j minus I. And as I vary n, as I vary I, it gives me all the possible places where it can start. So if I want a gap of length k, I just range from I to I plus k, and I divide by the total number of gaps, and this will give me the fraction. So the question is there an easy way to count how many times do we have a gap of length k in summing starting at I? Well, we can draw the picture, and we can say, okay, well, let's see. I know I have to take fi, I know I have to take fi plus k, and I can't take anything in between. I can't have fi minus 1, I can't have fi plus k plus 1, I can't have fn minus 1. And if you look at this, you see that this is essentially the same as counting Zeckendorf decompositions. If you look at the far left, I need to choose indices from f1 to fi. I have to choose fi. I can't choose anything adjacent. Well, that's just counting all the legal Zeckendorf decompositions whose largest sum is fi. And similarly for the last one, it's essentially the same problem. It's counting how many legal Zeckendorf decompositions do I have, but I just have to shift my indices down. I'm not going to go through the algebra, but when you're done, at the end of the day, you get it's just fn minus k minus 2 minus I times fi minus 1. So now we just have to sum these products of Fibonacci numbers. You can use Benet's formula and just look at the sum of the main terms. You can do some bookkeeping to say the other stuff doesn't really matter. And then when you take the limit, you'll get the geometric series formula. So it's really not too bad to prove that on average, you have geometric decay. So there's a lot of interesting properties about Zeckendorf decompositions. And so I want to talk about one of them, and this is going to lead to an interesting game that unfortunately I do not know how to fully resolve. If anybody here can figure it out, I will gladly pay $500 because I have wanted a proof of this for over a decade now. So we've talked many times about how every integer can be written as a sum of non-adjacent Fibonacci numbers. If I give you a number like 16, I can write that as 8 plus 8, or I could write it as 13 plus 3. And so there's more than one way to write numbers as sums of Fibonacci's. And in the interest of time, I'm going to just skip to something. Okay, so I'm doing 18. So for 18, I can write it as f6 plus f4, or I can write it as 13 plus 3 plus 2. The first one is the Zeckendorf decomposition. We notice it has 2 summons. The next one is not the Zeckendorf, it has 3 summons. And so you can ask, how do the number of summons vary as we look at the different decompositions? And it turns out that the Zeckendorf decomposition is summoned minimal. No decomposition uses fewer summons than the Zeckendorf. You might have another decomposition that has the same number of summons, but nothing is fewer. And so you could ask, what other recurrences are summoned minimal? I'm not going to go through the details, but it turns out if we again look at these generalized recurrence relations where the c's are non-negative integers, if we look at the coefficient of the c's, then it's summoned minimal if and only if the c's are non-increasing. Let me give you a quick proof of why the Zeckendorf decomposition is summoned minimal. So we're going to define a really good monovariant. So a monovariant is a quantity that can only change in one direction. So if we have some decomposition, if we have the first Fibonacci number b1 times and the last one bn times in our decomposition, we'll define the index to be this weighted sums of the number of times we have each. And then we move to a new decomposition by doing one of two things. If we have some index repeated twice, we replace it with fk plus 1 plus fk minus 2. So we would replace 8 and 8 with 13 and 3. You have to be a little bit careful because we don't have 2 1s in the beginning, so 2f2 becomes f3 plus f1. And then if we have 2 adjacent Fibonacci numbers in our decomposition, we can replace them with the next. And then what you just go through and you just do the algebra and you show that the new index is less than or equal to the old index. So every time we do one of these moves, we never increase the value of the index. And so if we're not at the Zeckendorf decomposition, we can keep playing this game, and eventually you will hit the Zeckendorf decomposition. And since the index never increased, notice that as we do this, we are never gaining summons. We have two FK, so we have two summons replaced with FK plus 1 plus FK minus 2. The number of summons didn't change in that step. But the other step, we went from 2 summons to 1 summon. So when we reach the Zeckendorf decomposition, no matter what decomposition we started with, we can't have gained any summons. So the Zeckendorf has to be summoned minimal. And so we can use this to create a game. So I'm going to call this the Zeckendorf game. And then my student, Caroline, are you on the call right now? Caroline, are you there? Okay, so it may be that my student has not made it onto the call. And if that's the case, then I will talk about her part. So I use this to create a game called the Zeckendorf game. And again, I'm going to show you some interesting results about it. There is a huge open question, which if anybody in the audience is able to solve, I will pay $500 for the answer to this. So it's a 2-player game. The last player to win moves. The last player to move wins. Sorry, it's 4 a.m. here. And you alternate. And the way it works is as follows. We start with bins that are the Fibonacci numbers, and we start with n tokens, and we put them all on the first bin, and everything else is empty. And then we just do the Fibonacci moves. If you have 2 pieces on the kth bin, you can replace it with a piece on the k plus first and one on the k minus second. And again, you have to be a little bit careful if you have something on 2 copies on F1, that becomes just 1 on F2. And then if you have something on 2 adjacent bins, FK and FK plus 1, you can remove the 2 tokens and put something on FK plus 2. And so you can ask, does the game end? How long does it take? For each N, who has the winning strategy? And what is the winning strategy? And so let's do a specific game to just hopefully give you a sense. So let's take the number 10. So we put 10 tokens at the first Fibonacci number. And so everything else is 0. And so there's only one possible move. We take 2 things on the first and we replace it with something on the second. So that's F1 plus F1 equals F2. And so now we'll have 8 tokens on the first and 1 token on the second. And notice that this is still going to be a decomposition of 10. 8 times 1 plus 1 times 2 is 10. We have 2 moves now. We could take 2 things on the 1 and put another token on the 2, or we could take something on the 1 and the 2 and put something on the 3. Let's take 2 things on the 1 and put something else on the 2. So now we'll have 6 on the first, 2 on the second. And again, it still sums to 10. 6 times 1 plus 2 times 2 is 10. We have, several possible moves now. Let's take the 2 tokens on F2 and split them and put something on F3 and F1. So now it's 7, 0, 1. We only have one possible move. Take 2 things on the first and put something on the second. So now it's 5, 1, 1. We have, we have a few possible moves. Let's take something on F2 and F3 and put something on F4. And again, we can just keep playing and playing and playing. And so eventually the game is going to end in the Zeckendorf decomposition. And in this particular string of moves, player 1 wins, and they won in 9 moves. And so I've recorded the moves. And you should hopefully be able to see on the screen that there's a blank line. And the reason is, instead of moving from the constraint 1, 2, 0, 1, what we did here is we took something from the first and the second, and we moved to something on the third. We could have instead taken the 2 tokens on the second and split. And the reason I wanted to show this is 2 different games with 10 tokens, but we had a different player winning each time. And so depending on how it's played, you can definitely have both players winning. So you can show that every game ends in finitely many moves. And the reason is this summon minimal property we mentioned earlier. It's essentially the same calculation. Every time you move, the index doesn't increase and it sometimes decreases. Rather than using the index where it's the number of copies times the index, it's actually a little bit better to use the number of copies times the square root of the index. Then it's a strict monovariant. It's strictly decreasing rather than non-increasing. Again, it's 4 a.m. here, so I'm not going to go through the algebra. It's on the slides if you're interested, where you just go through and you show that after every move, it strictly decreases. And because there's only finitely many possible decompositions as a sum of Fibonacci numbers equaling n, you have to eventually reach the point where you're the smallest you can be and the game will terminate. We have results about how many moves it will take before the game ends. We have results on what the fastest game is. We believe that if you just look at all possible games, the distribution of the number of moves converges to a Gaussian. If you play a random game, it should be a Gaussian, but we do not know that yet. If you play a random game, we believe each player wins about half. Player 2 has a winning strategy, as long as n is at least 2. So as long as n is greater than 2. If n is equal to 1, there's no move. If n equals 2, there's only one move. You take the two things on F1 and replace something on F2. Once n is at least 3, player 2 has a winning strategy. Unfortunately, the proof is non-constructive. And so I will give $500 to anybody who can come up with a constructive proof of what player 2's winning strategy is. Just for the Fibonacci game. You can generalize this to other occurrences. I just want to know what's going on for the Fibonacci game. Caroline, are you in the Zoom call now? Okay, I will keep going then. And so let me give you an example of how to analyze non-constructively what's happening. So there's a beautiful game called Chomp. And the way it works is you choose a circle and then you eat everything that's on the board, on this rectangular board, from that circle up and to the right. And whoever moves last loses. And so if you choose, for instance, the bottom left corner, you would eat everything. So clearly you do not want to be whoever moves last wins, because then player 1 would just win on their first turn. So the claim is that player 1 has a winning strategy whenever you have a board that's, at least, 2 dimensions, and at least, 2 by 2. And, the proof is as follows. If player 1 has a winning strategy, they should just play it. If not, we're going to do a parity argument, and they're going to steal player 2's winning strategy. So imagine player 2 has the winning strategy. So no matter where player 1 goes, there has to be a response for player 2 to keep player 2 on the path to victory. So if player 1 chooses the upper right corner, 1 dot is eaten, then there must be a place player 2 can move to and continue the path towards victory. So for definiteness, I just chose some place to say, let's imagine that's where player 2 should go to keep on the path towards victory and eat all of those. So what this is saying is, because we are assuming player 2 has the winning strategy and they took the right move, player 1 is now going, and this board state is a losing configuration for whoever moves next. Well, player 1 can steal player 2's strategy by saying, I'm not going to move in the upper right for my first turn. I'm going to go where you were going to go. And now it's the same board state, but you've changed who's moving next. And now player 2 is moving next, so player 2 will be the loser. We can do the same thing for the ZeckDecompGames game. And so the notation here, the exponent is just how many copies we have. So if we're doing n, the weighted sum should just be n. And then the wedge just means which Fibonacci numbers are involved. So the very bottom is we have n minus 7 copies of 1, 1 copy of 2, 1 copy of 5, and that does add up to n. And so I'm going to show you how player 2 can steal player 1's winning strategy if that was the case. So let's assume player 1 has the winning strategy. So I'm going to color things. This looks somewhat peachish on my screen. Peachish if player 1 has the winning strategy, and blue if player 2 has the winning strategy. So player 1 starts, and they have the winning strategy. There's only one possible move. They have to combine 2 1s and make a 2. because player one has the winning strategy, no matter what player two does, they're going to move to a place where player one still has the winning strategy. So there's two cases to analyze. In the interest of time, let's just analyze one. Let's assume that we will look at the case where player two 1 to the n minus 3 wedge 3. The other case is similar. And so now player one only has one possible move. They have to take two ones and make a 2, because the 1 and the 3 are too far apart. And now, no matter where player 2 goes, it still has to be winning configuration for 1. And now this is where things get interesting, because if we get to the next level, the 1 to the n minus 5 wedge 5, it turns out that's a configuration we saw at the previous level. But we've changed whose turn it is. And so once we've reached the square, because we've assumed that player one had the winning strategy, because we've changed by 1 whose turn it is, this is now a winning strategy for player 2. And then this just propagates back upwards. And so I won't go through all the details, but there's a lot of related questions you can ask. You can generalize to more players. You can generalize to other occurrences. And then we can try to simplify the game. Caroline, have you made it on?
Seems he not joined.
I'm sorry?
It seems he not joined. The student is not joined.
Okay, she's on. Okay. How much time do I have left?
Another 5 minutes.
5 minutes. Okay. So this is just enough time to try to explain how we can make this game easier to analyze. So I'm not going to go through all the details. I just want to try to talk a little bit about a simplification I made with my student. So this is joint work. We've presented it at the last so we'll be presenting it hopefully at the next Fibonacci conference. We've presented it at a few local conferences. How can we simplify the game? So we're going to create what's called the black hole ZeckDecompGames game. So whenever we're playing, once you get an index that's sufficiently large, you remove that chip from consideration and never look at it further. So for example, let's say the FN black hole variation is going to be once you have an index of m or greater, that piece is removed. So for F4, once you move something to index 4, it disappears. That means you only have the first 3 Fibonacci's, the first 3 bins involved. And this makes the game a lot easier to analyze. Now, it turns out that if you only have at most 3 indices, it's not so bad. Once you get more indices, then the game becomes harder to analyze. We unfortunately cannot analyze the black hole game for arbitrary m, but we can do it in the very beginning. And so what's nice is if we start off with, say, a triple ABC, one possibility is we could subtract 2 from A and increase the second one B by 1. So that's the move on the far left, all the way to taking something at C, and we could split it by removing 2 and putting something on A, and then we would have something on D, the next one. But because it's the black hole game, we won't be able to see anything on F4, and that vanishes. And so I'm not going to go through all the details. You could also make the game even more interesting by saying you start off with an empty board and you first set the game up by having the players alternate putting pieces down to construct the board. And we can analyze all of this. I'm not going to go through the details. The main idea is because we're only looking at the first 3 Fibonacci's, there's not that many possibilities. And so we have a lot of nice ability to keep track of what's going on without the algebra becoming overwhelming. And so I'm going to skip all the details, but the point is it's finite enough that we can analyze all the cases. There are not too many possibilities. And at the end of the day, we get nice results about who wins in which configuration. And so player 2 will win if n is congruent to certain things mod 16, while player 1 will win the other times, except of course for some interesting exceptions. And so again, I'm not going to go through all the analysis, and just if anybody's interested in seeing more details, Here is a list of several of the papers on the subject that we have written over the years. And then again, if you just go to my homepage or just email me sjm1@williams.edu, I would be thrilled to talk to anybody who's interested in trying to push these problems further. So thank you.
Hey, thanks. It's wonderful talk. You connected the Fibonacci numbers, some combinatorial problems, and some game. Connected to game theory also. Thank you.
My pleasure.
Yes. Yeah, and further, you introduced many prizes to the participants. I hope
Yes.
some of you come forward. We'll do some time and then get back to you. So, are there any questions, participants? Have any questions? So, I have few questions. One of them is that you found a formula P and K that n minus K choose K minus 1.
Yes.
Are there any formulas for other sequences also, like Lucas?
So that is a great question. So I just started working with one of my students to see could we get a formula for, say, the Fibonacci's, where Tn plus 1 is Tn plus Tn minus 1 plus Tn minus 2. And it turns out we get sums of multinomial coefficients. And we've done some preliminary calculations. We know it converges to a Gaussian because we can prove the case in that. I don't have a nice clean expression yet for this. We've tried using the online encyclopedia of integer sequences, the OEIS. And so if anybody is interested, you're trying to look at the Fibonacci case or something similar to see if we can get something close to them, that's exactly the next question you should be asking. So the answer is maybe. We have a formula involving sums of multinomial coefficients, sadly, products of multinomial coefficients. And so the question is just, does this reduce to something nice?
Another one is that at one place you wrote h1 equal to 1 and hn plus 1 is 10 times hm.
Yes.
So that sequence, that is super increasing sequence.
Yes.
So is there any trial for other super increasing sequences also this type of?
So there's a whole slew of different types of relations you can use of increasing sequences that will lead to generalized Zeckendorf behavior and whatnot. One of the things which I don't think I mentioned due to time, but it turns out that the Zeckendorf decomposition can be used as a way to define the Fibonacci numbers. They are the unique sequence of positive integers, increasing positive integers, such that every number can be written uniquely as a sum of non-adjacent terms. So if I start with 1, I can't get 2 using just 1, so I have to add 2. I can't get 3 because 1 and 2 are adjacent, so I add 3. But I don't need to add 4. 4 is just 1 plus 3. But I can't get 5, so I add 5. If I want to get 6, that's 1 plus 5, it's non-adjacent. If I want 7, it's 2 plus 5, non-adjacent. I can't get 8, that's 3 plus 5, so I have to add 8. So it turns out this is another way to define Fibonacci numbers. The Fibonacci numbers are the unique sequence of increasing integers such that every number can be written uniquely as a sum of non-adjacent terms. So there's a nice correspondence between these decomposition rules and definitions. So we were doing linear recurrences here. A natural question would be, well, what happens if we have something that's a nonlinear recurrence, and what kind of results can you do? So one of the fun examples we did was we did things involving factorials. And then there are other generalizations as well. So there's a lot of stuff you can do here. There's a lot of problems if people are interested.
Thank you for introducing so many problems. Yeah,
my pleasure. And I hope to hear from some of you.
Thank you. We'll end the session.
Okay, have a great day all.
Thank you, sir, for insightful and enlightening words. I also thank Professor Satyanarayanan Reddy for chairing the section. Now we have the paper presentation section. For the presentation section, let me now